DraftScience physics video, and so trying to get somebody to have a conversation. Somebody defends something, either the cranks to defend their crankery, or the authorities to defend the people, the sycophants to the authorities of conventional physics, whatever that is, to defend their unicorns. But nobody seems to want to do that in any kind of disciplined, you know, reasonable, useful, logical, step-by-step kind of way. So I can only do my part. My part is, yes, I'll not only tear down your theory, I'll defend my counter theory that I think is much more consistent with the evidence. So, so the Ken guy has posted. I haven't got to these secrets of light thing. They're probably just horrible. But anyway, Nature's Secret of Magnetism, and this one here, where he does the paramagnetic kind of stuff. So this is like related to, you drop a magnet through a copper pipe and it drops slower than a similar piece of stuff dropped down a pipe. Other non-paramagnetic materials, because it creates a field in the copper that creates another magnetic field, that, and the two fields cause they dampen each other, and so it takes longer for it to fall because it keeps making magnetism and breaking it and making it and breaking it, so to speak. So anyway, so this isn't really helpful. This video uses an hourglass to describe his hyperboloid-y stuff, and it just doesn't explain to you anything about why magnet A moves towards magnet B. There's just no explanation in his conversation about why the two things go together or fly apart. So I'll explain. So I'll play a little bit of this, but just mostly the end part, because it just does this usual thing. It just repeats the same stuff over and over and over, and it's all this, well, I'll play some of the language. I mean, it's just this useless centripetal, centripoodle, central diddly-daddly. See, there they are right there.
Why not do it yourself?
And
with Wix,
I hate these Wix commercials. Yeah,
You've
right.
been asked this question by a few people. The reaction of aluminum to having magnetic fields. Over here, by the way.
Right, so copper does the same thing. So over here is bismuth, has nothing to do with anything he's doing here, so I don't know why he has to keep pointing to his bismuth. I guess he has fun making it, so he wants to point to it for, because he bothered to make it. But I don't know, if he makes his own little bismuth ball and he doesn't scrape off the uneven, the stuff from the mold, you'd think he'd just take those, whatever that's, the castings, file the castings off to make your little bismuth ball a nice little round thing so it's pretty and such. But anyway, it doesn't really matter. So the idea is he's going to move this magnet across the aluminum foil, and the foil will move as he moves the magnet. Now, like I said, this effect is known. These are aluminum and copper will both do this thing where they use aluminum for like the train thing, to levitate trains, because they can make it magnetic by running magnets across it temporarily. It doesn't hold the magnetism, but temporarily it becomes magnetic. Alright, so you can see he's playing with the bismuth, and then he shows the copper plate, and he explains how when he drops that on his giant magnet, it floats down. It doesn't just fall down, it floats down. And yeah, this is all effects that most people in the know all that crap. And the part that he fails at here was, so he moves it here, which he showed the moving part, and then he covers it, and it takes a while before he lifts it up. So yeah, I don't know, he keeps playing with the bismuth, which is pointless. So we'll get to this part or so. So yeah, he moves it with the magnet. So that part's just, you know, we can understand that.
Magnetic properties and the diamagnetic properties. I showed you diamagnetic properties when I actually pushed it away.
Yeah, I'm just saying diamagnetic properties. It just doesn't say anything. You know, to me anyway, it doesn't say anything at all. It doesn't really explain that what diamagnetic means is that for a moment you're able to line up the atoms in the material, and they become magnetic, but it won't stay that way. It does it only while the field's active, and when the field goes away, they flex back to their natural condition.
Doing this is a demonstration of diamagnetic properties. I'm using the centrifugal edge of the...
So centrifugal edge, so you keep some of this edge, and I'll explain why the edge is important, but yeah, it's why it's different than the center here.
Could be a new post.
And you know, he has a whole bunch of stuff.
Sweep the aluminum along its way here. Those aren't air currents, okay? That's actually the...
I think it did hit it a few
vortex.
times.
So, since now I'm going to place the magnet and the center of the magnet over top of the aluminum, what's going to happen if I lift it up? Let's see. Yeah.
Okay, so part of the problem with this is that he's doing it on foam, so he's doing it on a porous surface, and then he's putting aluminum foil. Essentially, a vacuum is formed, and so it falls off slowly because there's essentially a seal between the thin material and the other material, and you know, so that's an air problem. But beyond that, when it does float away, it will float away slower, differently than it would if it was not paramagnetic. So just as the effect happens going down, it goes going away. But again, this is just like dropping the magnet through a aluminum pipe. It'll do the same thing. All right. So, you know, he obsesses about this edge of the magnet and all this. I mean, I'll play some down here maybe, and he gets into it. Maybe he says something. I just don't think he will.
But it's attracted to the centripetal point. Now, I'm going to show you something that is exactly what the copper plates do over top of the giant magnet. When you drop these huge, heavy copper plates over the top of the giant magnet, they'll flutter down really lightly like a feather. Aluminum will do the same. Why? Because the centrifugal magnetism is pushing against the aluminum like a jet is.
Alright, so we made this weird comparison, like a fire hose in a drain and all of this stuff, and none of this stuff is happening. The magnets aren't doing anything. They're converting the field energy, and how you orient something around them will change what field it's in, you know. And so this is what's really happening. Now, I know this drawing isn't going to be immediately it doesn't just scream, oh, I get it, you know. So you do have to think about it for a little bit. But magnets are two filters. And the really important thing to understand is they're acting completely independently. So even though they're stuck together, the north side and the south side, they're basically two different substances, and they're both receiving information from the environment and reacting. So you have to think of them as being almost independent even though they're tied together. So they both have a self-interest, so to speak. So when he does this thing with any magnets and foil and all the rest of this stuff, there's places where the north side might want to be attracted, but the south side is repulsive. And those two forces will balance. And that's what you end up with field lines. Field lines are essentially a description of, you know, what the fuck is with that? Every single fucking time I go to make a video, some douchebag has to type crap, and it's no doubt going to be crap. Yeah, blank images. Seen the light, white down to the side, red down, left side orange, whatever. Be blocking your IP, so be an asshole. So anyway, I just, you know, not interested, asshole. Come on, Gary, fire up the cam and get it to it. Fuck you. So somebody did make a 3D version of the two-slit experiment, but it's quite not very useful. Where the hell do I have that here somewhere? The little slit here. So, I mean, doing the 3/6 slit experiment, I don't know what that is. I don't know exactly why you're doing 3. This over here has some use because it has one slit, but you have the diffraction going the wrong way. It goes around the corner, not opposed to the corner. So these two things have to be moved. These parallel lines, it doesn't really work that way. This distance is tiny. It won't be represented at all at this end. So you have to just think of this as a big, huge magnifier. This magnifies what happens over here. So obviously this is really tiny and this is really big where you're projecting it. And so these parallel lines wouldn't even be visible. So they're essentially shining light to the same location if they have the same angle. And the point is that they don't have the same angle because the material on one side of the double slit is different than the material on the other side. The two...
Could be a new post.
I mean, some asshole's just saying, block me, Gary, please. You know, I will in a moment. Oh, shit. These people suck. I'm just so sick of this, you know, these assholes. If you're going to say anything, you should sign it. You should at least have the balls to do that. I mean, why would I give a fuck about your anonymous opinion, you dumb cunts? Yeah, I really don't care about anonymous assholes. What anonymous assholes have? What do the anonymous assholes have to say? Who fucking cares? Oh, yeah, audio notices off. Phew. Okay, back to work. Just really hate people.
Raising, you ever seen like a jet of water like push up a beach ball? So let's see if you can see this properly. Try it yourself. It'll actually push it off to one side or the other.
Yeah, so what's really happening, you know, is that it's not getting pushed off to one side or the other. It's that, well, the simplest part you can understand. I mean, I don't want to go into the whole polarization thing, but the point is one side of the magnet is creating something. Okay, when something goes through this, the south side, it gets changed, converted into something that it finds invisible. So if I put two, you know, if I put you know, a north against the north, the repulsion is because it's something they're sensitive to. So once it's converted to the same color as you are, you know, then you can see it and you move away from it. And the opposite effect happens when you're the north side and you have south side radiation coming out. That radiation goes right through you. So all of the polarizations of gravity are converted into something you'll find invisible. And then the opposite effect is all the polarizations of gravity are turned into something you're completely sensitive to. So it's just like a radio receiver. And so one side is receiving, you know, 10 hertz and one side is receiving 20 hertz, and they have the opposite effect on each other in the sense that if I'm producing 20 hertz, I'm sensitive to 20 hertz, and if I'm invisible to 10, so anything 10 goes right through me. I don't even know it exists. And the point is that if it doesn't know it exists, if I convert all of gravity, let's say, goes through a magnet, and it's getting, most of it is getting polarized to something that I find invisible, that means that the other gravity that's still out there that hasn't been converted is going to seem much stronger because I've eliminated all the counter. So all the red going in one side, now I've taken all the red out of the other side. You can sort of see that the reds are going to win. And so anyway, I don't really want to do the polarization argument. I want to just do the layering argument. And the point is that the center of the magnet has kind of a unique condition in the sense that there's no access from the red filter. So you can sort of see if something's sitting here, it can only receive black filtered it can't receive anything red filtered. There's no straight lines, don't allow the red filtering to get to anything here. But the point is that whatever's here is all, if it's going to be affected by a magnet, it has to be a magnet. There's no monopoles in nature, as they say, you know, at least for magnets. I don't think there is for electricity anyway, but so the point is that obviously the red side of the magnet and the black side, so the black side is going to be repelled and the red side is going to be attracted. So the red side is going to be swinging down. The black side, it's trying to get away from as fast as it's trying to get rid of it. And the point is it's going to end up doing that by sliding it in one direction or the other. So it's going to end up moving. If it moves this way, the attractive force isn't interrupted because there's still attractive force coming up from over here. So the attractive force isn't changed by moving this left and right. But what is changed is this repulsive force to the black is changed as it slides. It gets less and less significant. So, and especially when you get out to this edge, then all of a sudden now the black, which has now been moved to the right side, right? So now you have the black being the head, you know, the first shower, and this, now the red force will be able to affect the black and start pulling it down this way. So that's why you end up with a kind of a tendency for anything that's coming straight down to move to the side, is because of the repulsive element. The repulsive element still exists. So that's what I mean by the two things having an independent life. So even though this side is attracted, that means all this force here is pushing this down completely because there's no force it sees coming up. This other side is still exactly the opposite. And so the intensity is just as strong. And they say the repulsive end of a magnet, the repulsive effect is a little bit stronger than the attractive element. And so that would tend to mean that because this thing probably won't be able to line up perfectly straight, that it's going to tend to move in some direction or the other. It'll just pick one, whatever one there's a bias on, and it'll tend to move in that direction. And then especially when it gets somewhere past this perimeter and it can start feeling the effect of the south pole, then it'll start pulling even stronger to the edge. So it will, as soon as it crosses this barrier, then it's heading south quickly. But the problem is momentum. So once the magnet starts to move, it has momentum as a physical thing, and it has to overcome that. So you can sort of see this with this cheap experiment. It's upside down, I think. Alright, so anyway, so there's a little ball bearing here, right? So if I push him all the way over to the edge, okay, and then I just initiate, you can see it goes way over, way overshoots, okay, and then it comes back. So its momentum, its acceleration, takes it right past the field energy. So it gains so much acceleration that it goes all the way past the field energy where it wants to be, and it has to now make the return trip. So it has to destroy all of that acceleration and then re-accelerate back to the neutral. So that's the dampening thing. It has to dampen the momentum, and that's what happens in this case also. Once the magnet moves, it has momentum, and the momentum will take it past the stopping point. And so that's why you can have these weird effects. Like I said, as I pointed out the other day, if you take these little tiny magnets and you throw them at a big magnet, you'll find that you can make them do all kinds of not an orbit. You can't get a perfect circle out of it, but you can almost get them to do a half C. You can get some pretty eccentric path changes in the magnet. But there's nothing special about this edge except, so you have to also understand that the more of the filter the force is going through. So the force is coming from all directions. So you could just say this point is really this entire magnet has elements that end up in this point, where depending on where you are height-wise here, okay, this is, got to be careful how I say this one. Alright, so the closer I am here to this surface, then I start to lose this as significant. So the only field I can feel is this. Where at this corner, when I'm attached to it, it's going to seem stronger because all of this field still is in play, and it's especially the whole width of the magnet, so it's even the longest and strongest filtering. So this corner, even though it is accessible to some of this, almost accessible to this negative force, depending on how fat it is or big it is. Whoa, way too close. Sorry about that. Some videos just don't go the way you want them to. This is one of them. But the point is, you can sort of see that because of this angle, all these points are always relevant at close to the surface. Where close to the surface, you're really hard to get to. This part of the magnet becomes less and less relevant. So you will be stronger at the corner in terms of this force of attraction. But if the magnet sticks out at all, then you're going to have the problem of the repulsion being created by the red side. Because now it can get to you. Now it can reach you. But that's so the real point is that the magnet is essentially two separate filters, and they're affected independently by two separate kinds of force, and they produce the kind of force that affects inversely. They're invisible to the force they produce. So the north is producing field energy that north sides of magnets are sensitive to. That's what I meant to say. Yeah, so that's why they repel, is because they feel the force. Because it's a polarization, they are more likely to filter. And it's like the frisbees going through the jail bars. So the north side produces frisbees that are coming out exactly opposite to the orientation of the filter. So it's this ribbon. I used this ribbon argument before, but a ribbon, you turn it 45 degrees and it ends up with exact opposite dimensional orientation. Right? You can't get more opposite to horizontal than vertical, and yet they're only 45 degrees difference. It's not what you would expect, 180 degree difference. And so that's an interesting phenomenon. And that's the controlling element in all this. So let's see, do I need to say anything else? Yeah, so, I just don't want to do the video over, so I'm just not going to do it over. But it's one of those videos that could be done over. So I'll play a little more of this.
Everything in the universe is magnetic. Only four principles: resistance, capacitance, permeability, and permittivity.
Yeah, permeability, permittivity. So those you could understand as what I'm just saying, in the sense that you could say that when he says this permittivity and permeability thing, he's talking about acquiring acceleration and not acquiring it, being invisible to something and then being sensitive to something. Now the resistance and capacitance thing this really doesn't have much to do with any of this. It doesn't have anything to do with the creation of this force, and it's a real force, and it comes out in straight lines, just like gravity. Magnetism works the same way. That's how the field lines are created. It's because it's a straight line force that emanates from the magnet. And what else needs to be said about that? And so the neutral points are the interest one. The barrier between the two is where the magnet ends up having, you could sense that the field lines would line up, because the magnet is always. See, the trick of field lines is once they have material in them, they become magnetic themselves, and they create their own field line. So they change the field lines by being field lines. So the more material in the field lines, the location of the field lines is going to change. That's why it kind of clogs up at the north and the south end. But anyway, what else do I want to say? Because it just becomes part of the magnet. I mean, as the material piles up, it just all becomes part of the magnet, and it just makes the magnet bigger, in a sense. So the neutral is the interesting one. And if you take two magnets, and put them lengthwise and vertical wise on their center points, there is a point where you can have the two of them and you'll feel almost nothing, neither repulsion nor attraction, as you move them together, because all the forces end up balancing. But you have to do it, it has to be rather precise, and any jitter or any little bit off, and you can start to feel the magnet trying to turn or trying to twist to orient itself to the field. But that's what's happening, is the red side is doing what, it's like they're acting independently. Each one is going its own way. So when this black side is trying to get away, the red side is trying to come in, the two of them can be very competing in terms of their force. And they really don't affect each other, except in the sense that they're tied to each other. So then they just have to torque or balance their condition based on that torque. And that's where they end up with too much momentum. And that's when the magnet swings around, and then its momentum carries it too far, and it goes too far around, and then it has to dampen and go back again. And that's why the metal slows down going down, is because essentially you're initiating a magnetic field, and then the charge of that field swings too far, and then it has to reverse direction, and that's the dampening. So anyway, yeah, it's probably enough for this video. I don't want to just saying that his explanation doesn't explain anything, first off, and there is an explanation for the difference in these. The two sides of the magnets are different, but they're only different in the sense that they're creating something kind of opposite, but it's an opposite in the same thing. So it's just a let's see, don't know how to really, but there's no fundamental difference. They're both just a force, and one force is compatible and the other's incompatible inversely. So and that's why this whole thing ends up being neutral to gravity itself, is because both are neutralizing one part of gravity entirely, but then they're maximizing or doubling another part of gravity entirely. So it ends up balancing out, because they've made one thing twice as much, and when they made one thing nothing. So it ends up being the same when you have a random field. 1 plus 1 equals 2, and 2 plus 0 equals 2. So, same difference. Alright, so anyway, I've made better arguments on this magnetic thing, but this will have to do. So we'll call it a video. No, I got to finish doing the other gravity thing and whatnot, but I guess I want to watch his light videos and see what he says. Because, it doesn't make... The stuff he says just can't be defended. I mean, the constancy of the speed of light is just so well established, and we know it doesn't really change. It just gets the distance, how much distance light has to travel can change inside of a medium, but the speed isn't changing. So, anyway. Till next time and such, I think. Yeah, this will have to do. But I would like to be able to get into some kind of videos where we have actual questions and answers, instead of just sermons, by know-it-alls. Not good enough.